Today we're going to be talking about radian and degree measures. By the end of this video, you should be able to graph angles in degrees and radians, including coterminal angles, and you should be able to convert between radians and degrees, and you should be able to use formulas to solve real-world situations. So first, trigonometry, as originally started by the Greeks, was the study of triangles. In the 17th century, trigonometry was expanded to include functions that represented light and sound waves, orbits of planets, etc. Typically, in trigonometry, angles are represented by Greek letters. The most common ones are theta, which is an oval with a horizontal line through it, alpha, which looks like a little fish, and beta, which is a capital B with a tail. Let's start by taking a look at the standard position for an angle. When you have an angle in standard position, this is the initial side. This is the terminal side. The point here is the vertex, which is typically at 0, 0. And this is our angle. So if we look at a graph, the initial side is typically the positive x-axis, and then you go around counterclockwise. You all are familiar with degrees, so if we are starting here, this would be 90 degrees, this would be 180 degrees, this would be 270 degrees, and a full circle would be 360 degrees. Now, radians are in terms of pi, generally. If we start here on the positive x-axis as our initial side, there are 2 pi radians in an entire circle. And I'm going to use a little r as an exponent to represent radians for now. Later, we'll drop that and just assume that angles are in radians unless they are marked with the degree symbol. So if a whole circle is 2 pi, that means that half a circle is pi. So a quarter of a circle is 1/2 pi, or we generally write pi over 2. And 3/4 of a circle would be 3 pi over 2. Now let's take a look at some examples of angle measures. We have 6 different angles that are given here. We want to sketch these angles in standard position and then name the quadrant that the terminal side is in. So, standard position has the initial side on the positive x-axis. If theta is 300 degrees, well, we said above that going 3/4 of the way around the circle would be 270 degrees. So 300 degrees would be about here. And we want to mark that our angle is going this direction. Remember that the quadrants of a graph are 1, 2, 3, and 4. So the terminal side of this angle is in quadrant 4. And that's it for part A. Part B, we want 5/6 pi, or 5 pi over 6. We know that the initial side is going to be the positive x-axis. We know that going halfway around the circle is 1 pi. So 5 pi over 6 should be a little bit smaller of an angle than that. So about here. And that would be our angle alpha. The terminal side is in quadrant 2. Now with part C, you will notice that beta is negative 135 degrees, while our initial side does not change. The fact that our angle is negative means that we are changing direction. Instead of going counterclockwise, we're going to go clockwise 135 degrees. So this would be 90 degrees. This would be 180 degrees. So negative 135 degrees is about halfway between negative 90 and negative 180 degrees. And that is our angle beta. The terminal side is in quadrant 3. Let's go on to part D. We have that theta is negative pi over 4. Our initial side is still the positive x-axis. We said that a quarter of a circle is pi over 2, or 1/2 pi, which means that pi over 4 is going to be half of that. Since our angle is negative, we are going clockwise. So we want to go negative pi over 4. This is our angle theta. The terminal side here is in quadrant 4. Part E, we have that beta is 200 degrees. Initial side is still on the positive x-axis. Then we need to go 200 degrees counterclockwise. This is 180 degrees, so 200 degrees should be a little bit farther than that. So beta is this angle. The terminal side here is in quadrant 3. Finally, we need to find alpha is equal to 7 pi over 4. We have our initial side. We know that 2 pi is all the way around the circle. And 2 pi is 8 pi over 4. So 7 pi over 4 is not quite all the way around the circle. So if we break up this circle into 8 pieces, because a full revolution is going to give us 8 pi over 4s, that would be 1, 2, 3, 4, 5, 6, 7. So 7 pi over 4 should be in the middle of the fourth quadrant. Now, you might notice that theta in part D and alpha in part F look like they're in about the same position, and they are. These two are coterminal angles. Coterminal angles are angles that share the terminal side. So if we want to find one positive and one negative coterminal angle for theta equals 700 degrees, that means that we want to add or subtract 360 degrees, which is a full revolution of the circle. So since we have 700 degrees, if I subtract 360 degrees, I get 340. If I subtract 360 again, I get negative 20 degrees. So I'm looking for two angles, one positive and one negative, that have the same terminal side as theta equals 700 degrees. Well, 340 degrees and negative 20 degrees both have the same terminal side as 700. There are infinitely many answers to this, as we'll see in question 3, but those are two of the possible answers. For part B, we are given that alpha is 21 pi over 4. Since this is in radians, to find coterminal angles, we want to add or subtract 2 pi. As we saw earlier, 2 pi is the same as 8 pi over 4. So we need to add or subtract 8 pi over 4. So if I start subtracting, 21 pi over 4 minus 8 pi over 4 gives me 13 pi over 4. If I subtract 8 pi over 4 again, I get 5 pi over 4. If I subtract 8 pi over 4 again, I get negative 3 pi over 4. Technically, all of these are coterminal angles with 21 pi over 4. But I just need to pick one positive and one negative angle. So I pick these two. If I want to find all coterminal angles to beta equals 120 degrees, then that would mean I am adding or subtracting 360 degrees any number of times. I could add 360 degrees 27 times, or I could subtract 360 degrees 500 times, and those will still be coterminal angles with beta. So the way that I can write all of the coterminal angles is by saying 120 degrees plus 360 times k, where k is any integer, and I can write that as k is the element of z. And I have two lines on the diagonal. That is the symbol for the set of integers. If you don't want to use that notation, you can write out k is an integer. Now, let's talk about converting between degrees and radians. We know that 2 pi radians is equal to 360 degrees because those are both one full revolution around the circle. So, when I convert between degrees and radians, I'm going to use this and set up a proportion. But I can simplify this a little bit. If I divide both of these by 2, I get that pi radians is equal to 180 degrees. So if I want to convert 30 degrees to radians, I can just set up a proportion. I have 30 degrees is equal to some number of radians. And I know that 180 degrees is equal to pi radians. My suggestion when setting up your proportion is use the first fraction as what you're given and what you're trying to find, and the second fraction as your conversion factor. Then just make sure that either the degrees are both on top or the radians are both on top. Now we just solve by cross multiplying. So I get 30 pi equals 180 r. So r is 30 pi over 180, which simplifies to pi over 6. So that means that 30 degrees is the same as pi over 6 radians. I can do the same thing when going from radians to degrees. So if I know that I have 3 pi over 4 radians, I want to figure out what that is in degrees. Then I can use my conversion factor. I put the radians on top in the first fraction, so I need to put the radians on top in the second fraction. Then I can go ahead and cross multiply. So I get pi d equals 3 pi over 4 times 180. And this can be simplified. I end up with pi d equals 135 pi. If I divide both sides by pi, I end up with 135 degrees. So this means that 3 pi over 4 is the same as 135 degrees. Now let's take a look at some word problems. We're going to talk about arc length, angular velocity, linear velocity, and sector area. Arc length is represented by the formula S equals r theta, where S is the arc length, r is the radius, and theta is an angle. Angular velocity is represented by the Greek letter omega, which is a small w. Omega equals theta over t. So the angular velocity is the angle divided by time. Linear velocity, which we'll use the letter v for, is r theta over t. Radius times the angle over time. You can see that this is a combination of the first two formulas. You're either doing arc length over time, or you're doing the radius times the angular velocity. Our last formula is for sector area. A sector is like a pi wedge. It's part of a circle. Sector area is 1/2 r squared theta, where theta is an angle. The important thing in all of these formulas is that theta is in radians. So let's go ahead and take a look at some of these problems. Problem number 6 says, the second hand of a clock is 10.2 centimeters long. Find the angular velocity of the end of the second hand. So since we're trying to find angular velocity, we want to use this formula. The second hand goes all the way around the clock, so theta is going to be 2 pi, the full revolution. How long does it take the second hand to get around? Well, it takes 60 seconds for the second hand to go all the way around the clock. So if we simplify this, this means that omega is pi over 30 radians per second. Next, let's find the linear velocity of the end of the second hand. So linear velocity, we're going to use this formula in purple. So we are told that the radius is 10.2 centimeters, and we know that it goes all the way around the clock, which is 2 pi radians, in 60 seconds. So if we go ahead, throw this in the calculator, multiply everything together, we get that the velocity is approximately equal to 1.068. The units are centimeters per second because the length of the radius is given in centimeters and we are counting in 60 seconds. So that is our linear velocity. The last thing we want to look at is the area of the clock. So we're going to use this green formula for sector area. So we have area equals 1/2 radius, which is 10.2 centimeters squared, times theta. We're trying to find the area of the whole clock, so that's 2 pi radians. So if you look carefully, the 2 and the 1/2 will cancel out, and you just end up with the area is pi r squared, which is the formula for the area of a circle. If you throw this in your calculator, you get that the area is 326.851 centimeters squared. Remember, we're talking about area, so we have centimeters squared. Finally, we have a child is spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. So the fact that we are given this in revolutions per minute is going to be an issue. We need this to be in radians per minute or radians per second or radians instead of revolutions. So if we do a little bit of dimensional analysis, we have 180 revolutions per minute. We know 1 revolution is equal to 2 pi radians. Our goal is to have the units of revolution cross out and end up with radians per minute. So if we multiply this together, we get 360 pi radians per minute. So we're going to use this instead of the 180 revolutions per minute when we do our calculations. We want to find the angular velocity of the rock. Well, angular velocity is omega equals theta over t. The angular velocity is essentially what we just found up here. Our units are in radians per time. We have an angle divided by time. So we already did that work. The angular velocity is 360 pi radians per minute. Typically, angular velocity is in radians per second. So if you want to go ahead and convert that to radians per second, you can go right ahead. You would get 6 pi radians per second. But when we get to part B, we have fewer calculations if we leave it as radians per minute. Part B says, find the linear velocity of the rock when the rope is released. So we want the linear velocity, which is r theta over t. And then we want to convert our answer to miles per hour to see how fast this rock is traveling. So we know that the radius is 2 feet And then we already have our angular velocity, the theta over t. So we are multiplying by 360 pi radians per 1 minute. So we get 720 pi. This is feet per minute, because we had feet and we have minutes. We want to convert this to miles per hour. So we need to do dimensional analysis again. We start with feet per minute. I'm going to convert feet to miles first. I know that there are 5,280 feet in 1 mile. And again, I put this fraction this way so that the units of feet will cancel out. So now I have miles, which is what I want. Now I need to convert minutes to hours. So we know that there are 60 minutes in 1 hour. Again, the units that we do not want cancel out. So the minutes cancel, and we are left with miles per hour. So now we just need to throw this in our calculator, do 720 pi times 1 over 5,280 times 60, and we get approximately 25.704 miles per hour. So when this child lets go of the rope, that is how fast the rock is traveling.